All right, today we're diving into how AI is learning to have its own aha moments. Those flashes of insight that drive real discovery. There's this new project from Google Research called Mars, and it's basically teaching AI to stop just being a coder and start acting like a genuine research scientist. We're talking managing budgets, learning from failure, the whole shebang.
And really, it all comes down to this one big question, right? Can an AI actually learn to think like a scientist? I don't just mean spitting out code. I mean, can it strategize? Can it learn from its mistakes? Can it manage its resources and have those breakthrough insights that really push science forward?
Okay, so to really get why this is such a big deal, we have to look at the core problem. I mean, why is automating AI research so much tougher than just, automating regular software development? It turns out there's a huge roadblock. And this slide really gets to the heart of it. See, standard coding is pretty straightforward. It's often black and white. Either the code works or it doesn't. You can test it fast. But AI research, oh man, that's a totally different beast. The paper calls it a probabilistic resource-intensive endeavor, which is a fancy way of saying it's messy and expensive. You can literally spend days training a model just to get a teeny tiny improvement, and half the time you don't even know for sure what you did that made the difference. And because of that messiness, most AI agents right now are, well, they're pretty terrible researchers. They fail in three major ways. First, they totally ignore budgets. They'll just burn through time and compute power for the smallest gains. Second, they write this awful tangled code that's impossible to debug or reuse. And the biggest one, they have what's called the credit assignment problem. Basically, they can't figure out which of their ideas actually worked and which were duds. And if you can't learn from experience, you're not going to get very far. So to tackle all these problems, the researchers at Google came up with a completely new kind of agent. So let's meet our hero, Mars, the AI that's built to be a smart scientist. Now, this new framework from Google Cloud AI Research isn't just another bot that writes code. No, this was designed from the ground up, specifically to get over those exact hurdles we just talked about. And its name, Mars, basically tells you everything you need to know about its secret sauce. It stands for Modular Agent with Reflective Search. And trust me, each of those words is a hint at one of its superpowers. Let's break that down. You can think of Mars's whole scientific approach as being built on three main pillars. And it's these three things working together that let it act less like a dumb script and more like a seasoned researcher. Okay, pillar number one is budget-aware planning. So unlike other agents that will just chase after a 0.1% improvement no matter how much it costs, Mars is, well, it's thrifty. It gets that a model that takes 10 hours to train might be useless in the real world compared to one that's almost as good but only takes an hour. It's constantly doing that cost-benefit analysis. Next up, pillar two, modular construction. Remember that spaghetti code we talked about? Well, Mars doesn't do that. It acts like a professional software engineer. It designs a solution, breaks it down into clean, separate, testable pieces. This makes everything it builds way more robust, way easier to fix, and way easier to improve later on. And the third pillar, which might just be the most important one, is what they call comparative reflective memory. This is its secret weapon for solving that credit assignment problem. Think of it like a super detailed lab notebook. It's constantly comparing experiments, looking at the differences, and figuring out exactly what caused a result to get better or worse. It learns real lessons from both its successes and its failures. Okay, so with these three pillars in place, how does Mars actually do in the real world? Well, the researchers threw it into the deep end, a bunch of really tough machine learning competitions. And this is where we see its aha moment. Just look at this. It gives you a sense of how insanely complex this whole process is. Every little circle here is basically a different experiment. Mars is navigating this giant maze of possibilities, testing out different kinds of networks, fiddling with learning rates, you name it. And it's learning something from every single try. And then this happens. This is the aha moment. After trying tons of different things, Mars has a breakthrough. It takes a lesson it learned from one branch that totally failed, combines it with an idea from a completely different branch over here, and puts them together to create this new winning plan. I mean, that's exactly how human scientists make discoveries, right? By connecting ideas that nobody thought to connect before. And the results of that brilliant new plan? A final score of 0.656. Now, for anyone who knows the super competitive world of Kaggle competitions, you know that's a fantastic score. And it was good enough to earn Mars a silver medal, a real, tangible prize for its scientific process. So, how does Mars actually stack up against other top AI agents out there? Well, in a controlled head-to-head competition, the results are pretty staggering. Mars won a medal 56% of the time. That's a massive leap over its rivals. And it snagged a gold medal almost a third of the time.
I mean, this chart really says it all. When you put them all in the same environment with the same rules and resources, Mars isn't just a little bit better, it's playing in a completely different league compared to the other top agents.
And this success isn't just down to one magic feature. The researchers proved it by basically turning off its superpowers one by one to see what would happen. In these charts, that top green line is the full Mars system, firing on all cylinders. The other lines, that's what happens when you take away its organized coding, or its memory, or its budget awareness. Performance just tanks. It proves that all three pillars are absolutely crucial. So, what does all this mean? Why is this such a potential game changer for AI?
I think this quote from the paper just nails it. Mars isn't trying to write a single, perfect script. It's trying to build an optimal software repository. It's thinking like an engineer building a library of tools, not just a one-off program. It's a much more structured and professional way to think about research.
So, what are the big takeaways here? Well, for me, there are three. First, AI is really starting to evolve from just being a coder to being a partner that can actually plan and strategize. Second, Mars is so good because it copies the habits of the best human researchers. It's efficient, it's organized, and it learns from everything. And finally, this is way bigger than just winning coding competitions. Imagine applying this kind of scientific engine to things like medicine or discovering new materials. The potential is huge. And that really leaves us with a pretty mind-blowing question to think about. If an AI can truly master the scientific method and become a world-class researcher, what's the next great discovery it's going to unlock for us?
Okay, so we've all seen this, right? You give an AI a really tough problem, and it doesn't just spit out an answer. It actually shows you its work, laying out this whole step-by-step reasoning process. It's called a chain of thought, and it looks, well, incredibly human. But how is it really doing that? I mean, does it have a grand plan from the very start, or is it just making it up as it goes? That's the big mystery we're going to unpack today.
And that really brings us to the heart of the matter. When an AI starts to think, is it like a chess grandmaster who's already seen the whole game play out in their head, every move planned from start to finish? Or is it more like a genius jazz musician who just knows the very next note to play, improvising this beautiful melody one moment at a time? Is it a planner or an improviser?
Now, just so we're all on the same page, that step-by-step process, researchers have a name for it, chain of thought, or COT for short. It's the AI literally talking its way through a problem, and it's what makes these models so incredibly powerful. Figuring out how that actually works under the hood is the key to everything.
So, to crack this case, researchers knew they couldn't just look at the final answer. Nope. They needed a way to peek inside the AI's mind while it was working, to actually see what it was thinking at every single step of the journey.
And to do that, they built a special tool for the job called Tele-Lens. You can think of it like a super high-tech magnifying glass that lets them look right into the AI's internal state. At any point in that chain of reasoning, Tele-Lens let them just pause and ask the model, hey, what do you really know right now? And using Tele-Lens, they basically grilled the AI with three crucial questions at every step. First, do you know the final answer yet? Second, can you tell me what you're about to say next? And third, any clue how long this whole thinking process is going to take? The answers to these questions, well, they would become the clues that would solve the entire mystery.
All right, and this is where the real detective work kicks in. By looking at the AI's answers to those three questions, the researchers started to piece together the evidence and finally settle this planner versus improviser debate once and for all.
So the first big clue they were looking for was this. When does the AI actually figure out the final answer? Is it confident from the very beginning, or does that confidence bubble up somewhere later down the line? This graph tells such a fascinating story. That black line, that's tracking the AI's confidence in the right answer over time. And look at it, for almost the entire process, it's totally flat, just hovering around random chance. It basically has no clue. Then, all of a sudden, right at the end, that red bar, bam, a massive, dramatic spike in confidence. The AI doesn't know the answer all along. It has this sudden aha moment right before it gives it to you.
Okay, so the AI doesn't know the final answer from the get-go. But does it at least know the path it's going to take to get there? The next clue is all about foresight. How many steps into the future can the AI accurately predict its own reasoning?
And the evidence here is just as crystal clear. This chart shows how good the AI is at predicting its future steps. It's fantastic at guessing the very next word, sure, but look how fast those lines just plummet. After just 1 or 2 steps, its ability to see the future completely fades. It's not following a map. It's navigating in the dark with a tiny little flashlight.
And that brings us to the final piece of the puzzle. You know, if the AI were a real planner, it should have some sense of the entire journey from the beginning. So the question is, does it know how much work is ahead? Can it predict how long its own chain of thought is even going to be?
The answer here is a huge, resounding no. Just look at these heat maps. They compare the AI's predicted length with the actual length. If it were a perfect planner, you'd see a nice, bright diagonal line. Instead, it's a total mess. There is almost zero correlation. It's like the AI is starting a road trip without knowing if it's driving to the corner store or across the entire country.
So, let's review the evidence. The AI has no clue what the answer is until the very end. It has extremely limited foresight into its own thinking, and it has no idea how long the journey will take. I think it's time for the verdict.
All the evidence, it points overwhelmingly in one direction. The AI is not a master planner with a grand strategy. It's a brilliant improviser, focusing only on the very next, most logical step and discovering the path forward as it goes. And the researchers themselves came to this exact same conclusion. They found that these AI models operate with what they call a myopic horizon. Myopic as in nearsighted. The AI's entire thinking process is built to support the immediate, local step right in front of it, not some grand long-range plan. Now, this isn't just some fascinating academic finding. Understanding that AI is basically a short-sighted improviser has huge practical implications for how we use these tools, how we decide to trust them, and how we can make them way more efficient. So the first big implication is something called the wooden barrel principle, and it makes perfect sense. A wooden barrel can only hold as much water as its shortest wooden slat, right? Well, in the same way, the reliability of an AI's reasoning isn't about its average confidence, it's all about its most uncertain steps, its weakest links.
And this idea turns out to be incredibly useful. Instead of trying to measure the AI's confidence across thousands of steps, we can just zero in on the 5 or 10 most uncertain pivot points. And look at this table. Using Tele-Lens to focus only on those weakest links gives us a confidence score of 0.69. That's a full 9% more accurate at predicting if the AI is right or wrong. It's just a much smarter way to know when to trust the answer.
Okay, the second big implication is a really clever efficiency trick. I mean, if the AI is just improvising step by step, does it always need to go through the whole long song and dance? For simpler problems where it gets the gist of the answer early on, maybe we can just let it take a shortcut. This is what they call the caught bypass. By teaching the model to recognize when it has a pretty good idea of the answer early on, we can let it skip that whole long chain of thought process. And on some tasks, this happens over 16% of the time. That's a massive savings in computer power.
But here's the absolute kicker. You get that 16% speed up for almost nothing. The overall drop in accuracy is a tiny, negligible negative 0.03%. It's basically free speed, all by taking advantage of the AI's natural improvisational style.
So, we've learned that today's AI is less of a grand chess master and more of a brilliant but nearsighted jazz musician. And that leaves us with one final, really big question to think about. If AI can only really see one step ahead, what does that mean for solving the kind of grand challenges that require true, long-range foresight? Solving those, well, that might require a completely new kind of AI. All right, the AI race is really heating up. And Google, they just dropped a bombshell, a huge new milestone that could seriously change everything. We're talking about one single number that shows just how fast their AI, Gemini, is exploding in popularity. So, let's dive right in. Just look at that number, 750 million. What is that? Well, that is the number of people using Google's AI chatbot, Gemini, every single month. And look, this isn't just some big flashy number. No, this is a massive signal that people all over the world are jumping on board. So where did this number even come from? It's straight out of Google's latest earnings report for Q4 2025. And it tells a really incredible story about just how fast people are adopting this stuff. But, to really get what this milestone means, we got to break down what we're actually measuring here.
Okay, so what we're looking at here are monthly active users, or MAUs, as they call them in the tech world. This is basically the gold standard for figuring out if an app is a hit. Because think about it, it's not about how many people downloaded it once and then forgot about it. It's about how many people are coming back and using it consistently, month after month. And that's way, way more valuable.
But here's the thing. It's not just the sheer size of that 750 million user number that's blowing my mind. It's the speed. It's the velocity, how incredibly fast Gemini managed to get there.
I mean, get this. Just last quarter, Q3, Google said they had 650 million monthly active users. Fast forward to Q4, and boom, 750 million. That's 100 million new active users in just 3 months. That is some serious, serious momentum. It tells you something really big is going on with Gemini right now.
Of course, Google isn't operating in a vacuum, right? This growth is happening in what is probably the most competitive tech landscape we've ever seen. So the big question is, how does Gemini actually stack up against the other big players, the other heavyweights in the ring?
Okay, this chart really lays it all out for us. You can see Gemini there at 750 million. That is some serious traction. They're way ahead of Meta AI, which is sitting around 500 million. But, and this is a big but, they're still chasing their biggest rival, ChatGPT. OpenAI's chatbot has about 810 million monthly users. So yeah, the gap is definitely closing, but wow, this race is far from over.
So that begs the question, right? How in the world is Google closing that gap so fast? What's their secret sauce? What's the engine that's fueling this kind of insane growth against a giant like ChatGPT? Well, you can bet this isn't just happening by accident. This is all part of a very deliberate, very strategic plan from Google. So let's pull back the curtain and really break down the key pieces of their strategy here.
All right, it really boils down to 3 key things. First up, they launched Gemini 3. This is their most powerful model yet, and it's what they call natively multimodal. Fancy term, but it just means it can understand and reason across text, images, and even video all in one go. Super powerful. Second, they rolled out a new, cheaper subscription plan called Google AI Plus. The goal there is pretty clear. Turn all those free, casual users into paying customers. And third, and this is a big one, they're actually building their own custom hardware to run all this stuff, like the new Ironwood TPU chip. This is custom silicon made specifically to run their AI models, which is a direct shot at NVIDIA's dominance in the space.
And hey, don't just take my word for it. Google's own chief business officer, a guy named Philip Schindler, he laid it out plain and simple. He said they're focused on a free tier to get tons of people in the door and then subscriptions to, make some money. It's a classic 2-pronged attack. And based on the numbers we're seeing, yeah, it's definitely working.
Okay, so we've got users, we've got growth, but how does this all translate into actual money for a company as massive as Alphabet, Google's parent company? Let's connect the dots from user growth to actual revenue.
Check this out, $400 billion for the first time ever. That's what Alphabet pulled in for annual revenue. And a huge piece of that pie is coming from their AI division. You got to remember, every single one of those 750 million Gemini users is a potential subscriber. They're a source of incredibly valuable data to train the models. And they're a potential customer for all the other AI services Google is baking into its entire ecosystem.
And the CEO himself, Sundar Pichai, he's not shy about it. He directly connected the dots between launching the more advanced Gemini 3 and hitting the 750 million user milestone. For him, it's all one big, interconnected strategy, and it is clearly paying off in a massive, massive way.
So let's put it all together. You've got these incredibly powerful new models, you've got more affordable pricing to get people hooked, and you've got custom hardware coming down the pipeline. The big question is this enough? Is 2026 going to be the year that Gemini finally overtakes ChatGPT and takes the crown in this great AI race? I mean, with this kind of momentum, you have to wonder, what do you think is going to happen?
Have you ever wondered how an AI like OpenAI's Codex can feel like the exact same assistant, whether you're using it in a simple terminal or a really complex code editor? Well, today, we're going to pop the hood and see exactly how they pulled that off. All right, let's just jump right into the big engineering puzzle OpenAI was up against. Imagine you've built this incredibly powerful AI coding agent. The thing is a genius. But how do you get it to show up and work the same way everywhere? We're talking the commands line, a slick web app, and right inside your IDE like VS Code. That is a huge challenge. So here's the deal. Codex has to exist on all these different surfaces, as OpenAI calls them. You've got the CLI, a web app, an IDE extension, you name it.
And if you want users to have an experience that doesn't feel, totally disjointed, all of these phases have to be powered by the very same core logic. Now, you could try to rebuild the agent's brain for every single platform. And let's be honest, that's a recipe for disaster. It's inefficient, it's going to be full of bugs, and you'll never get a consistent feel. They even tried some early experiments, like using a generic messaging server for the VS Code extension, but it was clunky. It just wasn't the right tool for the job. They needed something much, much better. This search for a single unified approach led them to what I think is a really elegant solution. The absolute best way to think about it is like a universal translator for the AI agent itself. And here it is, the hero of our story, the Codex App Server. At its heart, it's a special kind of API, one that can talk back and forth, and it serves as the one and only connection between any app on the front end and the core brain of Codex on the back end. And yeah, this universal translator idea really is the perfect mental model. It doesn't matter what language the application is speaking, could be TypeScript in VS Code, JavaScript in a web browser, whatever. The app server takes those requests, translates them into a language the core agent understands, and then translates the agent's thoughts and actions right back. Of course, for any translator to actually work, everyone has to agree on a common language. So to make this all possible, OpenAI designed a communication protocol built on just a few simple but really powerful core concepts that any application can easily understand. And believe it or not, this entire complex system is built on just these three fundamental ideas: an item, a turn, and a thread. Seriously, every single thing that happens in a conversation with Codex can be described using these three building blocks. So let's break them down. First up, we have the item. Think of this as the atom of the conversation, the smallest possible piece. An item could be the message you type, it could be the agent showing its thought process, or it could be a chunk of code. The key thing is that every single item has a very clear start and a very clear end. That's super important for the UI. Okay, so once you have items, you can group them into a turn. A turn is basically one complete back and forth. It kicks off with your request, say, run all my tests, and it includes all the different items the agent generates until it has completely finished that job. And finally, all of those turns live inside a thread. The thread is the container for your entire session. It keeps a full history of the conversation, and because it's durable, you can literally pause what you're doing, close your laptop, come back a day later, and pick up right where you left off. It just works. What's so brilliant about this whole system is that it creates this incredibly rich, streaming interaction. Instead of you sending a request and just waiting for a final answer to pop up, the app server tells your client immediately that work has started. Then it streams back all the items as they happen. This is exactly why the agent feels so responsive and alive. So, we've got this really elegant protocol, but how do different apps actually plug into this Codex Harness in the real world? Well, the architecture is super flexible. For local apps like an IDE extension, the app server is just bundled right in and runs on your own machine. But for the web version, the app server runs in a container on OpenAI's remote servers. This is really clever because it means all the heavy lifting happens in the cloud, keeping the UI in your browser incredibly fast and lightweight. And this quote from the team really nails the killer feature of that web architecture. Because the agent's state, its memory, its progress, is all on the server, your work just keeps on going, even if your internet cuts out or you accidentally close the browser tab. You can just reconnect and boom, everything is right there waiting for you. Okay, so let's zoom out for a second. We've been down in the weeds with the technical details, but why is this standardized approach so important? What does it mean for the future of AI agents? Well, it matters because it creates a stable, first-class, officially supported way for anyone to build on top of Codex. Now, sure, there are other, more limited ways you could talk to the agent, but the app server is the real front door. It's the method you use if you want to build a truly rich, interactive, and powerful application. And that really brings us to the final, most exciting thought. What OpenAI has built here is essentially a universal power outlet for a really sophisticated AI agent. By standardizing the plug, they've made it so much easier for any developer anywhere to build new things with this technology. So the real question this leaves us with is, what happens next? What incredible new tools and applications are going to be built now that this powerful foundation is in place?